Hello, welcome back to the stream. I'm Junchan, and today we're back doing some Purescript and some graphs and Comonads as we've been doing for a while. So let's get to it. So last time we actually submitted a PR to the Purescript Alga library, and I saw we had a reply from Thomas. So let's take a look at it. Didn't mean to mark this really for review. Thanks for adding this. To be honest, I wrote the core of this in a few hours. So impressive, and haven't looked at it since. It's also unpublished, so if you're interested in implementing the library, don't want to have to wait on me, please feel free to take the code here and build on it in your own library. Otherwise, I'm happy to review and merge things here. You know what? I'd definitely love to have a experienced Purescripters feedback. So let's definitely offer the collaborative option. Thanks a lot. I'd be quite happy to have your feedback as I make progress with my exploration of the library. And I think I mentioned I didn't mention the Comonad, and hopefully succeeding in implementing a Comonad instance for it, as I did for FGL here. And FGL pull request, it's an L, I think was here. And okay, Control C and Control V. For learning purposes, in FGL here. There we go. So that's cool. Also, I saw CI didn't pass. I'm not sure what's up with that. Oh, CI didn't pass because we had a test to fix as our next to-do item. So excellent. Past June has left a red check mark for us current June to be looking at. So let's see whether we reproduce that here with a little Spago test maybe, and and take a look at the test. And here, yeah, that's where we were trying to make the executable graph from the Comonad of Graph Decompositions blog article to work for us. And what I was hoping is that when creating that specific shape there, let's put it in front of us here. When we do this shape, I would have thought that A would have both B and F as in its adjacency map or adjacency list. But it only has B, exactly like the directed version, if I remember correctly. So yeah, we're expecting BF, but we really only get B. So basically, it seems like our UG circuit, oh, maybe circuit needs to be changed actually. I didn't consider that. Circuit and path. So let's go take a look at that. Circuit, whoopsie. Not what I wanted to do. Oh yeah, I started remapping here. It's going to be annoying while things are a little bit in flux. Okay, so circuit uses path, and so path uses edges, and edges takes a sorry, that's edge set. Edges, it takes a list of tuple, then unquery edge, and creates overlays from that. Okay, so okay, let's do some intermediary steps here to understand what's going on. First, I think I'll want to maybe just do a super simple case like edge and understand how it's represented underneath in the adjacency map and take it from there. Okay, so let's do a little graph that will be UG edge from, let's say, true to false, and I think that's probably enough. And then what do we want to do with it? Maybe the UG adjacency list. Maybe we'll also try adjacency map. I don't know. And then we'll show that, or log show rather. And yep, that seems like that's possible. And it gives us tuple false with an empty list and tuple true linked to false. So we already have something that's unexpected here. So so let's try and dig a bit. So G is a UG, undirected graph, so it's it doesn't have a show instance, but that's fine. To indirected also just a wrapper with a UG. We don't mind too much. From undirected, that's worthy of giving a shot. So let's try that. So let's do log show of, I think, adjacency list this time, which is going to be the graph version. You know what? I'm not going to accept that. And we're going to do that on from undirected of G, but I think it would be UG dot from undirected of G. Okay, that looks believable. Let's give it a shot. And that's the same thing. So that's already something that's a little bit weird. So, well, we have one option, which is to go into two relation, but I mean, yeah, it seems like two relation is a piece of the puzzle there, because it's supposed to be symmetric relations. And after all, otherwise this UG is only doing a wrapping. And adjacency list here uses two adjacency map, which uses this for G. I suppose we could try two adjacency map as well. And then that leads us, I suppose, to try and troubleshoot our fold G, our local fold G here. And you know what? I think I'm not sure that that's going to help us so much either. Let's just clarify what two adjacency map gives us, though. What's the error here? Unknown value. Or maybe it's not exported. No, it's not exported. Let's export it. And now we don't have a map we don't have a show instance for adjacency map. Yeah, so I don't know whether this is the right path to pursue. Probably not. Okay. Let's keep that around. So I suppose I really need to, instead of just trying the functions, I think, well, I could actually also check that it does the thing we expect in Haskell. And is that what I did last time? H true false, overlay H false true. And that gave me false, 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 true, and true, true. Yeah, but that we want something different here. We want G prime equals just H true false. And that's just H false true. Which is in the other direction, by the way, which is strange. But yeah, that doesn't sound very undirected to me. Let's do adjacency list G prime. Ah, yeah, no, that's good. So definitely we want that, and that works. So let's go check. Let's go check the adjacency list code for undirected graphs in the Alga original Alga library, and see whether we missed something. Okay, we missed using our muscle memory to be able to do things properly when we shift here. Adjacency list is here. Oh, take this. It has nothing to do with, so yeah. So basically I made a mistake here. I copied the graph functions over to get started on the undirected version, but really what I should have been doing is going down the list of a function here and re-implementing them in Haskell, in Purescript. So let's see whether we have enough building blocks here to do this. And does this compile? It does not. So we don't have R, but maybe that's because we import qualified and R. Oh no, maybe we just don't have our adjacency list. We don't, because we made it very minimal. Okay, so we definitely have missed some follow through power here. So relationship symmetric is that the one? No, that's not the one. Okay, so we have relation here, but we don't have the symmetric open, or maybe it's here. No. Okay, a bunch of completely unrelated errors. And let's go back there. We can get rid of that. And then, yes, in Alga here, if we go to the content and relation symmetric and the source code, we should have adjacency list. This indeed we do, and it's just okay. It's coerce. We've tried to use coerce, but it didn't work very well for us. But this might we know how to deal with it, so it should be okay. And that's going to be a list of tuple of A and of list of A. Is that right? Is that what our adjacency list type looks like list of tuple A and list of A? Yes, it is. Okay, and so let's continue. And what we're hearing here is that no, is that we want to use the one from relation, which we do import as R. So that's fine. We import r.relation, and I think we just wrap it in SR, and then we're happy, right? And except we might have to do it with the pointful, like so. And we'll need to import list, which is not too difficult. Except indeed it is not the standard list. That's the standard tuple. Come on. Okay. Import data.tuple and EQ. I'm not importing prelude. I see. Where did ord come from then? That's not clear. And so our oh, it's not our relation. It's our adjacency list. Which doesn't exist yet. So let's go and build it. And let's take the same type signature here. And relation is relation here. And then let's go to relation right, not here, but here. And adjacency list is here, and that seems good. That seems like that's actually code we can use. So let's copy it and let's use the proper type signature for Purescript, and then try to rewrite this in Purescript, which is some actual Purescript coding. So let's give it a shot. So this is the section, the tuple section of empty list. I think we can rewrite this like that, and that's an empty list. And yeah, I don't know how to build one. I think did you say it was an internal? Yes. And then that's true. That's this diff list version. So we're probably gonna need some helper empty thingy there, or just do from array, I suppose, is the other option. Yeah, you know what? Let's take the simple route today and say from array. Okay. And then here we have tuple x z's. This is a section. I think this might work as an anonymous function, and then another tuple here, which we'll then need to parenthesize. And okay, what's that? Type class instance for show. What? No, I'm not reading correctly. Anonymous function argument appears in unvalid contexts. So we don't know which contexts. Therefore, we are going to have to let's see whether actually, oh, it's 41. Yeah, no, we don't know. It doesn't really tell us. Does Spago build tell us? No, it doesn't. It's between those things. Yeah, okay, great. Well, in that case, we'll just make them pointful and with a named argument. Okay, so that seems to be one of the ones, and then I suppose we can import data EQ. And those are in the prelude, so it's don't know that there's a lot of advantage to it like that. Well, yeah, definitely not a lot, because then we don't have map. So you know what? Let's remove EQ and ord there, and we need to import that. We do import that tuple, but we need to import not just the class of the constructor, and then a known value. Oh yeah, okay, indeed. Okay, yes, I did not put that in the right place. This is where it should be, I believe. Yes, and then yes, we pattern matching on a, I believe, a list to ask list. So well, it depends. do we have that set function? Let's go see what it returned in Purescript. Set. Okay, let's search for to ask a list. Do we use a special set? We do not. Okay, set. Set is in Purescript lists. I didn't realize that was the case. Where are we getting sets from? Ordered collections, I'm sure. Yes, most probably. And to ask, yeah, it's not there. So it's just that the type checker hasn't yet gotten to it. Okay, so we'll probably need to use something like, so it's going to be something like r.domain is a set. And then we apply, we want a foldable from it. So we could say to unfoldable, I suppose. I believe so. And then choose which unfoldable we want to use, and probably want to use an array. And then, but then we can't do pattern matching on head and tail like that. But the bad news is that I also don't know how to do it like cleanly like that in Purescript either. Okay, Purescript pattern match list head tail. Okay, so it will work with the list. So so maybe two unfoldable is sufficient then. Except that I might need to do a two unfoldable instance of the internal list we use. Or just use from array again. Or to array. Yeah, because this doesn't have the column constructor. And therefore, yeah, but we are stuck here. Because if we use an array, we can't pattern match on head and tail easily. If we use a list, since we use this list, we are in trouble. There is an unfoldable instance though, that's nice. That's very nice. But then I suppose we say, okay, we say array, and then, but it's not going to be efficient, by the way. If we head and tail on an array, not going to be as efficient as maybe even the list. Actually, can't we even that internal list, right? But that internal list, I don't know how to think about it so much. Is there an alias here? Okay, oopsie. Infix something? No. Yeah, I'm just wondering what that what this was here. Oh, it's the array. Oh wow, that's a column for array construction. Okay, let's do the Purescript way. Use it in JavaScript way, but let's take a look at whether there's some ways to pattern match on an array. And I think we just need to case, right? I think yeah, case and cons, I think is yeah, is what we need to do. Yeah, okay. So all right, that's R, and then we case and cons are off, and we just head X, tell these, and then do that. And we indent a bit. And nothing, well, is dealt with up there, actually. So we just refactor this, I suppose. Nothing. This leads to empty list. That sounds believable. And then, well, the fact that it ignores the ES is not really a problem. I mean, I don't actually know whether the ordering matters, but let's do this. And then we could further rework it, but let's just try this. And so this is the array on cons. Yeah. And span, I don't know what what that is actually. I don't know what span is. Span. Okay, who are you, span? It's Hugel maybe. Yeah, that looks believable. A predicate, editable, and a list, and then returning a tuple of AA. Okay, yeah, that sounds completely believable. We just need to find whether there's a span for array, and there is, and it deconstructs into init and rest, however, but that's fine. So let's get span array, and let's deconstruct that into an init and a rest, and make sure it's a tuple. And I think in that case we can deal with that. All right, and that should be a list constructor. Yes, so actually that's also not going to be so happy because we want to build an empty list of the internal list style. I suppose we could use the the various instances. We have a monoid instance, so we could use memty there, or even empty if we wanted to be a little bit more fancy. I think memty is probably fine. And then how do we construct? I'm not sure how we build. We might have to use the list constructor, and I mean, ideally, I'd create some kind of constructor for this. Let's see how our friends, the Haskellers, do it. All right, content and internal. And we can use the applicative instance. Oh, that's cool. I suppose that's we just needed to read the docs, and it's probably also here, but it's hard to read. Yeah, applicative instance, pure something something. Yeah, it's really hard to read. Okay, great. Let's try it. So you're saying we mapend pure of that with pure of that, and then you're saying that this is memty. Okay. All right. Yeah, that's actually one of the things we needed to fix. And apparently you're not happy with... yeah, of course, because you have a dot there and you need a compose. Okay, and now what? Now apparently we get a tuple back and we wanted an array, or we get an array and we wanted a tuple. So here we have a tuple, so that's fine, right? We kind of need to figure out the type of our go, to be honest. Will the compiler be kind enough to tell us? It is not, at least not Purescript ID. Let's see whether spec build is. It is. It's a T0. Okay. So okay, great. So I think we say this was a list, because and in our domain we have what? We have a set of A, so that should just be a list of A, I think. And then we pass that the list of relations, and that is going to be a list of tuple AA, I believe. And what do we return? Where we return whatever is probably going to be the type of the return of the argument here, the return type. And so if we save, does this compile? It does. And then we see, well, that's not a list right there. That's not, how do we pattern match on an empty list? Yeah, well, that's a very good question. And I think we basically have to say sort of equal empty or something, like case it on equal empty and true false, something like that, right? So case es equals empty of, and then true here will give us this guy, and then false will give us this guy. And then we can get rid of that and hope it types checks. Yeah. Right. Good point. So true unfoldable could go to a list, but we sort of said actually it was an array, and that's totally fine. And then we have the same problem, but let's see, I'm not sure whether that's the return type that constrains us or not. Do we want to say that this is array as well? It doesn't matter so much, I don't think. Oh, is these the same as is here? Okay, let me go back to the Haskell code for a second here. These was actually R. Yeah. But we still have some trouble. Maybe we want to say from array here as well? No. Yeah, no, right. Let's drink a bit. Yeah. So the fact that we map over an array here, yeah, of course, to from array here. And it doesn't work. I could not match list T1 with type A0 or with type tuple A0. That's so sad. Look at how tight and concise this is. Do I need to give a type to this list of A? No. Hold on. Oh, it's the reverse. It's the reverse. Yes, indeed. And yes equal empty there. No, false. So therefore, list array. Okay, so probably the same. Or not. Span wants an array. ES doesn't have an array. Yeah, I suppose we want to do we want to make this an array as well, and that's really easy because we can just say that it is, and then it should be fine. Yes, indeed. Okay, and there, however, V's is going to be an array. So yeah, but that's fine. Tuple of, is that in the right X and map second wise? I'm trying to map in those things. And you want this to be list tuple A0, list A0, but you have array A0 instead. So we put a tuple A list A at the front, so that's the head, and then we put another list A at the head. So is it more like this actually? No. Okay, let's look at the documentation again. Empty corresponds to empty list, and two lists can be concatenated with mapend. Okay, so maybe we just say that's it, and we just concatenate it. No. Singleton lists can be constructed using the function pure. So two lists concatenated. So then yes, pure, but apparently still not. But more for a question of list and array this time rather than something else. So maybe that's fine. Is it fine? It could be because of these then. What is the type of these? Yeah, no, this is array. So we do pass these that are arrays because they're unconsts. And these and these are both arrays. And therefore this should be a list, but you say you want an array. Why would you want an array? Is it because of wise? It might be because of this map second wise, that this might be an array actually. Wise is where? Wise is the init, so indeed it is an array. And so we'll want to do from array on it. And we type check, almost. Cannot match record with relation. So that might just be that we need to unpack that guy because it's a new type. And we compile. Oh yeah. And so now in theory, we don't only compile, but we should maybe have a passing test, and that would be amazing. Except we have some problem with symmetric relations apparently. But this should now compile, no? Yeah, it does. So come on, give it a shot. No, you don't. Okay. G. Oh. Right. So yes. Of course, that's not in this direction at all. It's in this direction there. SRG. Yeah, that compiles. But not all the way. And directed. Come on, yeah. But no type class instance was shown from that, but that's fine. We don't need it. Where are we? We have we're not good. That's not right yet. And that's also not passing. Okay, well, you know, slowly. I would have thought that undirected adjacency list there, now that it's two relation, our adjacency list would have actually solved the problem for us, but it hasn't. But I'm still expecting what we see in Haskell, which is false, true, true, false. But here we have false, empty, true, false. I should probably just have that as a test, shouldn't I? Undirected graph. It makes a simple undirected edge, which will be something like ug.adjacency list of ug.edge of a true false and should equal from array tuple true, from array false, tuple false, from array true. And I think we could use a singleton there, but that's be fine. And we test, and maybe we remove those things. Yes, so we are not yet where we want to be, and there might be also a some sorting to do here. Okay, so what's going on? UG adjacency list is this guy. Uses toRelation, which is this guy. Undirected toRelation. Right here. Which uses 4G over RMT, rvertex, overlay, and those are all R.relation A, and R being the symmetric relation. Symmetric relation R. Symmetric relation R. So probably 4G is the culprit. 4G is supposed to be coerce, and here instead of coercing, we've re-implemented the graph version. That sounds fine. I suppose that the fact that we 4G over the symmetric relation should be sufficient to then, when using, so maybe it's not about that. So can we print relations or something? Can we? Not really, right? Not really. It's shadowed, okay. Doesn't matter. But yeah, I feel that that's the problem. Here we use our adjacency list. That's supposed to be the symmetric one, which uses the non-symmetric one. Is it really that simple? Yeah, it's just the coerce, right? We implemented that. I wonder if to ask list whether that's really the same as set to unfoldable here. I would think it is, but I think we're going to debug trace. We don't have that. Spago install debug. And I think we can spy somewhere in here, maybe. And maybe we need forget what spy is like exactly. Felt to, ooh, that's not nice. What felt to run purse graph? A debug, maybe it's not debug trace. Maybe it's just debug. Or maybe not. Okay, let's go check out the Purescript debug. Debug. Indeed, there's no debug trace, it's just debug. But visibly, are we going to need to? There we go. And spies seem to just well, No, it doesn't just work. It needs SPI needs a string. Yes. So that's which one is it? It's relation dot adjacency list. Okay, and test. And that's just a function, of course, isn't it? So what are we going to spy on more precisely? Probably these guys then, like maybe how about our domain and our relations. Our relation. Yeah, that's pretty good. Yeah, except we probably want to restrict our tests to this guy only. Can we do that in Purescript spec? Running a subset of the spec, focus, excellent. Can we focus on it? It only, yes we can. Oh, not that, not that. It only. Already, I'm going to have to import that. It's fine. Okay, so now we have only that really simple test working, which should make things easier to troubleshoot. Indeed, what do we have? So in the first run of Go, the relation comes in and it has false on one side, true on the other, and then some other empty thing. That's the set. That's the domain set. Okay, and then a relation which is only true and false, or a tuple from true to false. Okay, and on the second run, right, there's two types of sets. Are we introspecting the set here? Maybe it'd be easier if I we're seeing the very low level representation of the set. Is there less a SPI that uses show? Yeah, I think SPI width might be where we would want then, and then we'd use the show instance for set, right? That might be a little bit more readable. But there's no show instance for set. Because there's no show instance for the, yeah, right, because we don't have, okay, fine. We add a show constraint just for debugging. And apparently it's still unhappy with that. Debug function usage, yeah, that's fine. In symmetric, oh, okay, I see. Now we need to have those everywhere. That's a little bit problematic. It's going to also go into adjacency list, but for now, let's just accept that tidy thing. Adjacency list. I believe it does go up to here, right? 2, 4, yeah. showing. Very untidy, but it should run, right? Yeah. And we have a more pretty thing to look at. Okay, so we have domain being false true at the beginning, relation being tuple true false. And yeah, no, I don't think it's actually doing the it only property. It's actually doing the next thing. Okay, that's fine. So it means it's only iterating once, I think. Yeah, there we go. It's cleaner. So but then adjacency list doesn't seem to be doing what we want. But the question is, are we relying on something that's coming from set to ask list that is not in the unfoldable instance? How do we find that out? Not here. Adjacency list set. Let's look at the Google to ask list from the set instance. But the set to an ascending list of elements subject to this region. Yeah, no. Yeah, I suppose the question is, why would this doesn't seem to have like something to make things symmetric, and so therefore if we just pass this through, how would that somehow make the relation symmetric? I don't know. So let's look again at the symmetric relation here, and it says it coerces the normal relation. And we see adjacency list edge 1, 2 is 1, 2, 2, 1, which is what we want. And here adjacency list 1, 2 is only 1, 2, 2, nothing, which is also what we want. So how would coercing be sufficient to magically do that? I have no idea. That's a little bit magic. Hold on. Unless course was something that was in fact not a library course, but a course that was just, no, there's data course right there. Don't understand that. How would just coercing an adjacency list, which is really this internal list. I suppose only maybe if list has some coercing code. Course. There are some utilities here, but this is mostly for coercing higher kinded things, I think. And so I don't know. I don't understand how only coercing are. Okay, let's double check here. R.adjacency lists in my mind is the regular relation R, right? This is the assumption here. Algebra graph relation as R. Okay. Only other thing that I could see is that we're not using the latest version of the library. That's a possibility. No, 0.5. And here, I don't know how I would know. Yeah, I need to maybe look up in the, actually I need to look into the Cabal file, right? That did I open that? I might not have. but maybe I can have a new window. I can go fetch for it. It's in iOS libraries Arga. Open folder. Shared space build code as libraries Arga. And yeah, just open that and tell me what you have. You have version 0.7. Okay, that's strange. Algebraic graphs 0.5. There is something strange going on. So let's go fish out the same code here. Coding question is that we believe that undirected HS is specifically the adjacency graph function list uses r.adjacencies, uses toRelation, which is defined here with 4G with the symmetric relation. Let's double check that this is also what we have with Purescript. 4G on the symmetric relation is toRelation. I've checked this before, but I need to check it again. And the R is over the symmetric relation, yes. I'm still a little bit unsure about our 4G, but then the other option is our adjacency list, which is the symmetric adjacency list, and our adjacency list. There's some specialization and inlining going on there, but we can ignore that. Is going to be the symmetric relation adjacency list, and apparently that's just coerce. And relation adjacency list is what we were just working on. And apparently just by magic that should make a difference between those two results, and I don't understand how. 1, 2, 2, 1. So the only thing I see, that's what I missed. Set to ask list edge set right there. Is it? I don't know. Maybe. Connect folder, connect empty. This and two symmetric R edges. Yeah, there's a bunch of stuff there that I don't think I've implemented in Purescript yet. Yes, indeed. That looks like that's just a copy of relation. Okay, good. Progress. So, where are the differences? So, empty. Okay. Oh, there's symmetry closure. That's that sounds like that would be very important. So let's start with from symmetric. From symmetric is just the data constructor, so nothing to see here. To symmetric, we don't seem to be needing to use it right away. Empty is just the coerce, that's fine. Vertex, also the coerce, that's also fine. Apparently, we don't even use edge here. But okay, that's a bit strange. But look at that, that's adding the symmetric. So obviously, that's where things are going to play out. But then the question is, where is that used? And the answer is in connect, I believe. because yeah, I think that's the missing constructor, and that does the more ambitious version of what Edge does here in a simpler fashion. So I think that once we have this figured out, then it should work. Okay, let's try. So b-click is what is one of the things we're going to need, and vertex list is the other. So let's start writing those, and b-click is what? It avoids the call to asymmetric. No, it's to do. Optimize by avoiding the call to asymmetric closure. So indeed, we do use the to symmetric. It makes a lot of sense to me, even though I don't exactly understand yet what this does. What I'm imagining is that it's just, you know, making sure all the arrows are present reversed, which is good because that's exactly what doesn't happen yet. I mean, one of the important aspects here, though, is to symmetric, really. That's, I think, is the workhorse here. So we need to work that because it actually uses our by click. So that must be, that is clearly not direction dependent. Okay, so we need to have by click here. And that's not too hard. The by click on two lists of vertices relation. I feel like I should start to bring up, I think I started doing that, actually bringing up the documentation. The b-click or by click on two lists of vertices with a pretty heavy complexity there, so there's a kind of bit of a cost there to do undirected graphs, interestingly enough. Interesting. And so by click x1, x2, y1, y2 are all of the edges. So are x1 connected to x1 connected to y1, x1 connected to y2, x2 connected to y1, x2 connected to y2. Yeah, so it just fully connects two things, but don't fully connect them between them. Okay, yeah, that's good. So that's going to be, hold on. That's not the internal representation. That's not the list that comes, that's the prelude list, isn't it? Yeah, it is the prelude list. Because the prelude is not imported because we're in Haskell, it's always there. So okay, so for us it's going to be what? I suppose it depends how we call by click, and we call it we call it in symmetric with two symmetric and x's, and so, and those look like lists too. They're really list of nodes, right? Do we need to do the same thing as with unfoldables that was done with the regular graphs? I suppose if we look at the constructions, then there's some that take lists as input. Mostly things take lists for construction. Yeah, lists, and those are the internal lists, which doesn't make things easy, but it is what it is, right? Yeah. So why doesn't this use the internal lists? We will not know, but let's make them array for now and see whether that works. So that's array A, and that's array A. And it's going to help to know whether set union in Purescript returns or works with, in that case, not arrays, but set from list. So we are going to want, again, two unfoldable. And we're probably going to be fine. No, from unfoldable. So that means we're actually polymorphic in the unfoldable here. So maybe we should just make the most general thing and be proud of us for following the advices of the smarter people. And then union. We're smart, but we don't have muscle memory. Data set is imported as set, so set union works, and set Cartesian product. Come on, be there, be there. It's not there. How about product? Oh no. Set Cartesian product isn't there. So let's look at the Hugel Cartesian product type and see whether it's a set of tuple AB. Okay, it's really not hard to write, but wouldn't it be nice if it had been there? It is not there. Oh, come on. So it's not there in ordered collections. Union with absurd, yeah. And some forks. Let's see if some people have done some hidden Cartesian product work. I mean, if I do one, it's not going to be fast. And we're doing something that's not going to be fast inside something that's probably also already not fast, not super optimized. But let's try to write it here. We're going to have to test it if we want to use it. Okay, so let's look at how things are implemented here. Let's go take a look at tests and see whether there's actually some running map tests, set tests. Okay. Oh, data, yeah, set. And yeah, nothing that looks like that. And so what are we going to do? We probably need to look at the implementation of something like union. No, not non-empty set. And union, yeah, text set M1, and then works with the underlying maps. Right, so what's going on with the maps? Is there a Cartesian product for the maps? Tuple. Submap. What was that? Pop. No. From foldable with full submap. Some tuple in here, but two unfoldable unordered. Yeah, that was it. So no, the answer is there is no such thing. So which means we how is the Haskell one implemented? Becomes the next question. and it uses the underlying representation right there of the set as this whatever immutable functional data structure thingy with a bin and a tip. Size balance trees. OM conjectured. Yeah. And it uses map monotonic and for bins and otherwise get merge set. And we need to understand what merge set is. So we'll just do something stupid, huh? I mean, for now at least. It is really the workhorse of what I was talking about, right? Because this x1, y1, xy1, x1, y2, that's exactly the Cartesian product of the edges. The union of the vertices and the Cartesian product of the edges. It makes complete sense. Shall we do a little Purescript Cartesian product set search? Cartesian. Okay, that's a big miss in spelling. Cartesian product set. Cartesian product in Purescript set. Okay, so it's not in ordered collection, but it's in Purescript set. And yeah, I kind of like that. That's nice. That's probably not efficient, but that sounds simple. So let's do that. Set, and I think there's those are maps underneath, and then maybe we can do from foldable. And so it uses the monad instance, I think, of the of list, which is smart, which might be smart enough to be fast. I think it's equivalent to a list comprehension. M1. And y is going to be this dot foldable m2. Yeah, I'm not so sure that it's going to be fast, to be honest. Maybe with array it might be a little bit faster. I don't know. And xy. Okay, so we're going to need to indeed import the data constructor set, but for that, yeah, we just need to do this. It's fine. And no, because it probably doesn't export it. Let's check. Indeed, doesn't export it. Okay, so so S1, S2. And maybe we can do from foldable. That might be set from foldable. And then, well, maybe it's just set from foldable. Well, yes, it is actually. And then we can just import the unfoldable class. What? I thought this existed from, okay, I see. It's two unfoldable that we want, I believe, here. Yes. And we're missing some ORD constraint. Yeah, I think that's very That makes sense. And a yeah. So no. So it's not that. It is too unfoldable here. Because we wanted to sort of go to something that has like the monad, the list monad behavior, and then here, well, here, yeah, from foldable should work actually, but apparently you need a foldable instance for what? I think it's just that you can't, maybe you need to know that this is going to be a list, I think. A list of A. And we need to import lists, and okay, that's pretty good. F, A, and F. And okay, so we start with something that's foldable. So it should be, oh no, oh, yeah, okay, fine, foldable. Forget what I said just earlier. Here, and then import that. Okay, and then you're unioning X with Y. And you can make it into relation because you need to be told that this is a domain, and therefore we can get rid of the parents, and that this is a relation. And then you compile. And now we have a okay, now we have a big biclick in relation. We have a biclick in symmetric relations, but we need the two symmetric implementation. So where is it? Symmetric relations. Two symmetric. It's just something that refers to, again, the regular relation. So ord A r dot relation A to relation A. And to symmetric SR, and then r dot, and that's hard to write. And okay, see, it's hard to write, and it's going to be useful to have it to write it here because we need it from here now. And so what is it? What is symmetric closure in relations? It's that thing. Symmetric closure of X is the overlay of X with the transpose of X, but what's the transpose of X? XY. Okay, so it doesn't make sure just that all thing of a click are connected to another. It makes sure that everything that has an arrow has the arrow back. So that's really the undirected bit, by the way. But I suppose, yeah, I suppose you also need to do the by click thing. Anyway, let's see whether we can work that one out. And I'm going to drink a bit. And yeah, I think we can get to finish the undirected graphs, but I'll take a tiny break and be right back. Okay, and we're back, and we're doing the symmetric closure. So we're pattern matching on the regular relation here. So yeah, that's not going to work for us. We're going to need to say domain and relation, I think. Relation, yeah. And then we also, when we build it, we're going to need to say actually domain, and then relation is R set union set map swap R. Well, maybe that's well, swap map relation, and who knows, that might just work, except for the syntax error, and that's actually relation to, and then we need to have Purescript types. But yes, it does. So now we have symmetric closure, and so we have two symmetric, and if we have two symmetric, then we also have by click. And here we are saying that we now have a foldable f of A. Hopefully that will work for us. And then apparently we needed vertex list 2 in order to wrap up this connect that we're trying to write. And vertex list has, we're in symmetric, yes. So vertex list is right here. And apparently it's just coerce, but we're gonna need again one for relations. So what is it? And that sounds super simple, so that's awesome. And we can just copy paste it. And do the Purescript things. And maybe we'll need to make it a foldable too, which is probably a good idea. foldable F, and so we need to have an F as well, and then our set would be to, well, unfoldable. How about that? Yes, and then we'll need that, and that's not going to work. I think we need there's a special syntax for that, isn't it? This relation with record. Yeah, that's fine. We can just do domain and then domain, and it should work, right? Except for the new type wrapper. And you don't seem to believe that it's a set. It is a set. What's going on? Vertex list, set, FA. Well, actually, we don't even need a dot. Yes, that's it. So we have vertex lists, and then we need the vertex X for symmetric things, and that's just for AF, foldable F, relation A to FA. Very annoying. And vertex list. And we probably need to have to do the same thing. Yeah, I believe we are. SR of R is going to be SR of R dot vertex list of R. And then we just need to import foldable. And then we need to fix that chorus right there. That's because we're going to have an SRX and an SRY, and we can just rewrap the whole thing into an SR once we're done. And by click apparently won't work. Why not? Conflicting definitions from different modules. I see. That's because we import R. Then we should be hiding things, or adjacency map. Yeah, that's wrong. And then cannot match type relation with type F0. Yeah, no, of course. In this case, it's completely just vertex list, right? No. Oh, because you need unfoldable, not foldable for that. Is that right? Yes. So we need to import it. And here F is not defined, so we'll define it. And here we have conflicting things about relations. So what are they? Let's go check out connect again from here. Connect is right, it's not here, connect is here. So we chorus this whole thing, and I think that here the problem with the type is our connect XY. Our connect should take an X and a Y. Do we have connect? We do, and we can make it a little bit more Purescripty here. And it takes relations and an ORD, so there's no problem here in appearance. It could just be, yeah, it's probably just that the association there that just doesn't work. The parents. Or not. So maybe it's about overlay. Yeah, because we use overlay here rather than our overlay. Ah, so when we chorus, we actually do chorus only that thing. Okay, I see. Interesting. That's a bit weird, but yeah, no, that sounds about right. Except that now we're trying to do a vertex list on the Y without chorusing this time. I see. Because we have vertex list for the whole thing. So we're going to need to say Rx at and Ry at. And then say that this is Rx and this is Ry. And that's still not going to make things happy because now we have foldable. That's a bit of an issue. And that kind of makes sense. Maybe we just need to drop all that shenanigan and make things arrays. And let's do that. It might work with other hinge types, but this would be simpler. And this compiles. And we didn't even need to change the types of the other things. And then automatically, maybe, it's going to work. How would it work? It would work because undirected, when we call edge, uses connect. And therefore, the connect is going to be oh, yeah, so no, that's not going to work. So show me the undirected graph connect. And it's probably going to be right here, and it is gconnect. Okay, let's run the tests. Maybe we fixed it already. Or we have not. Ah, false, true, true, false. Hold on. No, we do. We have. Yes. False, true, true, false. True, false, false, true. So it is just the ordering problem. So we did fix it. Okay, I will understand how in a second. False, true, true. I think we could do this more correctly by sorting both and comparing the sort, but look at it. It compiles, right? I mean, it compiles, it passes. And then, what about this guy? So let's see whether it's just an ordering thing. ABF, ABF, BACF, BCF. Okay, let's check the diagram here. BACF, we want BACF, but we only have BCF. Okay. Hold on, is it me that wrote CF? Yes. So it's me that wrote CF. So I made my test wrong. Cool. And then we want CD, but no, it's CBD. CBD, of course. So it should be CBD. Don't know what I did with this test. And then D should be EFC, right? And I just said E. Okay. FC. And then E should just be D. So that's fine. And F should be ABD. A, not AB, not ABD. Okay, how about that one? Almost, I'm sure. ABF, BACF, CBD, D is CE or EFC? Let's see. D is, yes, CFE, right? D. Some weirdness here. But I need to make sure that I'm constructing this correctly too, right? Because I'm constructing it from what I think is a circuit between ABF, and then overlaying with a path that's BCDE. Yeah, so F and D are not connected if I do it like that. So it is correct. It's just that I haven't represented the graph correctly. Excellent. Excellent, excellent. So how could we create that BD connection? Well, I suppose we could just overlay it with a BD and then would be done. Overlay with a UG.edge BD. Not BD, FT. FT. So that's not exactly going to work because of association. And then that's apparently going to be an issue too. So we need to do it like this. And that does seem to work. And still not, because of just ordering. So instead of EFC, we want CEF. Which is by alphabetical order, which is nice. I don't know whether that's actually a guarantee here. But I think this passes. Oh yeah. Excellent. So yeah, perfect. So we were missing a little connection there. We see that it's pretty easy with this syntax to add a connection. Let's make things just a tiny bit, maybe hopefully readable, by doing something like so, like we actually doing UG overlay of a circuit and a path and an edge, and then we're making that equal to a thing. Yeah, I think maybe like this will be acceptable, like that. Nice. So undirected graphs are there. Definitely not efficient. Also, we haven't contributed back our little where was it, Cartesian product shenanigans. We don't even know whether that's fast or not. We still have some debugging code, so let's at least get rid of the debugging code. The show instances that are needed because of that. Here. Not here. Maybe here. No. Okay, maybe here. Yeah. I think that must have been the remaining one, hopefully. Let's do a little sweep. Yeah, sounds actually pretty believable right there. Cool. And then we need to not import debug trace. Debug. We can also therefore remove it from our packages. And okay. That's not a bad. It's not a bad place to end. Yeah. So. Finish undirected graphs. And yeah, that's just a fork, right? And then I can add a little comment. That is not where we were working. This is here. Ah, yeah, like our tests are going to pass now. Hopefully, finish undirected graphs. I think undirected graphs work now. I had to implement probably very inefficient Cartesian product, set Cartesian product. And only implemented what I needed for simple undirected for simple tests, but what? But I think basically that's enough for now. Fix the tests. Yeah, maybe starting to move the docs would be nice, but maybe that could be a separate PR, and then we can do the Comonad. Okay, so let's see what Thomas thinks of that. Can I suggest to review this first, and then maybe do a docs PR? Basically pasting the docs from Alga, and it would be nice to maybe have it on Purescript then, if it's possible these days. Cheers. Okay, so that's nice. That will lead us to do actual Comonads next time on undirected, focused or pointed graphs. We'll see how we call those. Just a little tiny thing before I take off. Total maps. On the Purescript Discord, there was something that just came up that was about total maps, Haskell. Basically a way to, the package was not total map. It has something called dgraphy. It was not name, not tag. Okay, so key maps, justified containers, that's the guy. So that's that seems really interesting, and I kind of want to try it because example number 5. So let me, before going to example number 5, let me go to first example. So if we create a map with a tuple of a key of 1 and a string of 0 mapped to a key of hello, a key of 2 mapped to a value of world, then what this data map justified allows to do is to basically pass along some kind of evidence that the key is present once you validated that it is. So you basically start by saying member one table, and then you know that if you're in this branch just key that actually there is a one in that map, then everything that's below that can now be said to have had evidence of the key's presence. And that library apparently implements a zero-cost abstraction to then make sure that you never have to use maybes anymore. Like you can, everything that's underneath this branch can now be said to have the evidence past that one is a member. And that's pretty cool, right? But they now extend this to adjacency maps. And so, for instance, with directed graph, you're now able to say, actually, if, for instance, in this list that has nodes defined 1 to 5, I add a node 6 to my adjacencies. So let's say to 4, I say add me the edge towards node 6. But hold on, you say there's no node 6. Exactly. So there's no node 6. So what can you do? Well, you use with recmap, and kind of automatically will tell you the following edge is missing target 4 to 6. So it's a way to, it's not exactly graphs that are correct by construction, which Alga is, but it's a way to have adjacency lists that are correct by construction, which is pretty cool. So I don't know, because with Alga we are we are correct by construction, so we're never going to be able to actually create a graph using our connect and overlays and edges that actually ends up having like these kind of dangling edges. But I like that, and maybe in FGL, maybe it could be a pass sort of before building up a graph. I don't know, but I want to put it in the list because I think it's really cool. And I want to try it, and I want to see whether it can be done in Purescript or not. Okay, so source is maybe not the way to go, but synopsis example 5 is. So can we check adjacency list or maps? For correctness before importing them or something. In truth, it's kind of the reverse. Usually you use an adjacency map as the underlying data type to make things fast. Yeah, I just want to think a little bit more about that. I think this is quite helpful as a validation pass on data that maybe you want to import that is formatted as an adjacency map. And yeah, it's, I don't know actually from Alga, like, can you, I mean, clearly we can create Alga graphs from our adjacency maps, right? So let's take a look at this graph. There is a from adjacency map, right? From what am I doing? From a not. How about adjacency map subgraph? Let's see, how is it connected? I mean, I think a graph, oh no, a graph is this thing. Yeah, and I don't know exactly what is the relationship with these graphs and adjacency maps as is, like how this turns out to be then implemented with an adjacency map. I have no idea how that works precisely. So we need to figure that out, actually. That's really also a concrete next step. That's after that. So how are agents, damn, it's hard to say, C maps used under Alga? Yeah, we want to know that. Right now, I don't understand how that works. And then we can use the correctness. I mean, actually, just try to understand how the Haskell code works. I think there's no equivalent library in Purescript, but we can just think a little bit about it. Also see whether there's other algorithms for checking correctness of adjacency maps. And that's it. That's it for today. We will continue on Thursday. Building up a Comonad, maybe doing some of those stray things that are listed here. Maybe doing labeled graphs, but maybe at this point I will switch back to actually trying to use this notion of like rotating on a graph to do something maybe more visual, like try to maybe like there's something that I've been wanting to do, which is to give a shot at some of the D3 wrapping DSLs that have been discussed a little bit in the Purescript Discord. And that, or maybe some other visualization approach to lay out a graph and then sort of move the focus, like basically using the comonadic instance, or maybe more like creating a graph comonad that has more than the extract and duplicate code, that has some like moving capability. And then once we have that moving capability, then use that to sort of represent moving through a graph and staying centered on the node that we're focused on. I want to have a visual representation of that. And then we can then maybe go back to labeled graphs and then maybe start looking also at the performance. So let me write this down somewhere into here, Purescript React Explore. I think to me it kind of works in knowledge management, because graphs are really part of that in my view. I mean, at least for the things that I'm interested in looking at. So graphs, graph Comonads, Purescript, FGL, and Purescript Alga. Not Agla, I think I've been doing that often. And visualization of graph rotations. I think that's, and we're saying maybe D3 or maybe something else. Could be Flare, to be honest. We can see. All right, thanks a lot for watching. I am Junchan, and we've been doing some Purescript and some Comonads, and we'll be back doing that on Thursday evening. Thanks for watching, and bye-bye.